do it. Okay, live. Ready to go here. Okay, so let's get to it after reviewing the fact that Columbia developed Stan with a lot of grants. Actually, RStanArm that we're talking about today, I don't think specifically has, but Columbia doesn't distinguish between the different types of Stan. It uses Stan, not so much RStanArm, but Stan in general. Outside of Columbia, that creates the appearance of a conflict of interest. You can also see that downloads of RStanArm have been pretty rapid, probably almost 800 per day these days. That fact was not mentioned in Billions, but Stan was. So we're going to start to be talking about RStanArm today. Oh, and
were there any papers left on? It's not mine, but anything else. Student exams. No, not on this wouldn't be.
no.
Oh, thank you. I'm very sorry for
All right. Talking about RStanArm starting today. This basically marks the point where this class starts to get easier. I would say the most of March. It's mostly about how to call the functions, and this pretty much amounts to copying the code from the slides or the vignette or something like that, and then tweaking a little bit so it works with your data, with things like RStanArm that are packages that come with Stan models. We can get output draws from the posterior distribution relatively quickly and easily, and so we can start learning how what to do with the output of a Stan program, but you still need to be connecting it back to what we've slogged through the first 5 weeks or so in terms of how to think about these things in terms of probability, prior predictive distributions, priors, all those sorts of things. So one point that we talked about Thursday in the context of the homework, but it was, I thought, sufficiently important to go over it again, the different types of testing procedures that all go under the banner of frequentist, even though they're very different things. So historically, it essentially starts with Fisher, who would have a point hypothesis in the context of an experiment that the treatment effect was 0. But there was no other hypothesis to contrast this with. Consequently, you didn't make any sort of a decision or a conclusion, but you could calculate the p-value, which would be interpreted as a unit-free measure of evidence against the null hypothesis that the treatment has no effect. And some people thought, a lot of people thought, that was insufficiently ambitious. They didn't know what to do with it once they said, okay, well, there's a whole bunch of evidence this has no effect. That doesn't tell you anything about, or doesn't tell you enough about whether you should try the experiment on a larger scale or anything like that. And so the Neyman-Pearson approach was intended to address that and intended to leave the researcher in a situation that there's exactly one parameter that you should use as your estimate going forward. And that was formulated with a point hypothesis, often that theta is 0, but it doesn't have to be, in contrast with the second hypothesis, which was also a point hypothesis. And this has always seemed a little bit not entirely satisfying to me or a lot of other people, that it says, okay, well, we can get to one estimate at the end that we can go forward with, provided you as the researcher can eliminate all but 2 at the beginning. So you have 2 point hypotheses, either theta is 0 or theta is 42. And I think probably the best case to be made for using something like this was on the homework, where you say, okay, we have this data, we don't know, we have strong reason to think it came from one or of two people who have very different parameters in their data generating process, and our conclusion is like which person generated these data. But there's not a lot of situations in the social science where the task is like who generated these data among exactly two people. But anyway, you can construct a statistic, preferably a likelihood ratio statistic, and what makes this different from some of the other procedures is, well, yes, you put the likelihood conditional on hypothesis 1 in the numerator, the likelihood conditional on hypothesis 2 in the denominator. So the test statistic actually involves parameters conditioned on under both the hypothesis 1 and the hypothesis 2. And so you can calibrate the thing so that you'll only reject hypothesis 1 5% of the time when in fact it's true. The likelihood ratio has the benefit that among tests that control the type 1 error rate, it has the most power, which is to say the lowest type 2 error rate. But other than that, power isn't considered as an important characteristic as controlling the type 1 error rate. And so this does get you down to one number, and it answers the question that researchers, applied researchers, are always asking, which is how do I proceed after having conducted the study? The Neyman and Pearson will get you to an answer, but it has some arbitrariness along the way in terms of only considering two alternatives. And alternative 1 is for some reason kind of the baseline that you control the power on. Then a lot of people in economics, but this is, I guess, primarily attributed to David Hendry, develop this procedure. If you want to select a model, you should start with the most general model that you want to estimate and test down. So the null hypothesis in a situation like this is that some special case of a more general model holds, often by setting one of the coefficients to 0. The alternative hypothesis is that theta is in some interval. It's not exactly equal to the null value, and therefore if you reject the null hypothesis in favor of the alternative hypothesis, then you should stick with the more general model instead of going to a special case that nests it. Now, from the frequentist perspective, that is a better approach than starting with a simple model and then adding more complication to it, in the sense that you can get a consistent sequence of tests. With the Bayesian approach with supervised learning, it's kind of the opposite. But anyway, from the frequentist perspective, this is a procedure to choose a model. Maybe you land on the right model, maybe you don't, but it doesn't tell you what to do. How do I proceed after having conducted the study once I've concluded which model to use? Because you're going to have estimates of the coefficients within those models, and they're going to have uncertainty, and so it's not really a sufficient answer either, although arguably it's sufficient for choosing a model among nested submodels. So, and for many decades, it's been changing a little bit recently. The applied researcher community, inclusive of journals, inclusive of grant making agencies and stuff like that, have gone to this approach that no one really explicitly advocates, but you still have a point null hypothesis, oftentimes that some parameter is 0, and you have more likely to have a one-sided alternative hypothesis. Either the true parameter is greater or less than the null value that you specify, and then if your p-value for that test, which only involves the model under the null hypothesis, is sufficiently small, then you reject the null hypothesis in favor of the alternative hypothesis. But in order to answer the question, or if that's just where you stopped, then it would be insufficient, I think, for a lot of applied science because it wouldn't tell you, what to do. I've rejected the null hypothesis that theta is 0 in favor of the alternative hypothesis that, let's say, theta is positive, but just, concluding that theta is positive is often inadequate. You need to know something about the magnitude and things like that. And so they go a step farther and say, well, if you reject the null hypothesis in favor of the alternative hypothesis, then what you're allowed to do is proceed as if your point estimate of theta, namely theta hat, is the true value going forward in terms of evaluating the substantive implications of that. And that's not something that anyone could advocate from a frequentist perspective, because theta hat is a random variable, and essentially what this last procedure does is that, well, if you can reject your null hypothesis, then you get to pretend that theta hat was pre-specified as the other hypothesis in the Neyman-Pearson framework. And so in the real Neyman-Pearson framework, the second hypothesis is a constant. In this pseudo frequentist, it's not even frequentist, but just pseudo frequentist procedure that has prevailed for a long, long time, you're taking this random variable theta and pretending it was a pre-specified constant. And so there's really no coherence or argument for that. It's just, it satisfied the need of researchers to, how do I proceed after having conducted the study? There's a lot of people, even today, but certainly historically, that thought quantitative methods should be like a recipe. Like step 1, step 2, step 3, step 4, step, however many. And at the end of the steps, you have one number, and that's what you sort of take to be the truth as far as evaluating the substantive implications. But really, science, quantitative methods is nothing, like that, or there's no reason to restrict things that way. And so you might say, okay, well, there's a problem with this, in addition to it having no foundation at all, that, theta is just a point estimate. There should be some uncertainty around that. And so, a lot of people take this one step farther, or one step downward, or I don't know what, and say, well, if you reject the null hypothesis in favor of the alternative hypothesis, then you get to pretend that theta hat is the center of a normal distribution that you obtained by a Bayesian procedure all along. So take the standard error around that and call that a posterior standard deviation. Throw in a pony. Why not? You're just making things up at this point. And if you take this a step farther and say, well, theta is the center of a normal distribution that's my posterior distribution, you've now basically said, okay, well, you can use maximum likelihood to come up with a Bayesian conclusion, even though maximum likelihood is what Fisher created at the beginning in order to kill the Bayesian approach to inference in science in the first place. And so that should raise some alarm bells that something has gone completely out of whack along the way in terms of the evolution to what Fisher and Neyman-Pearson said, which I don't know that they were great ideas, but they were respectable ideas and contradictory ideas within the frequentist approach to things that has been watered down and distorted completely to where, what goes under the name frequentist these days in applied statistics really has nothing to do with the frequentist definition of probability or their approach to inference. And basically, we're going to talk about RStanArm starting in a second, is that, for most of the things where people are doing this stuff, it is basically just as easy to do the Bayesian approach for real. And then you don't have this problems where you're contradicting the frequentist approach by, doing something that's quasi-frequentist, quasi-Bayesian. You can just, do it entirely Bayesian from the start, and you get a perfectly coherent, albeit subjective, answer. And we want to, continue to think about, well, how do I proceed after having conducted the study? You're basically proceeding as if your posterior distribution represents your current state of beliefs about the parameters, and proceeding with the same probabilistic form of inference that got you to this point in terms of evaluating the utility or the substantive implications of a theory, but it's not going to be based on just like one point. It should be based on the entire probability distribution, because we need an entire probability distribution to capture our uncertainty about the parameters after having done the study, which all of these things which end in a point estimate don't do unless you pretend that they're Bayesian, and if you're willing to do that, you might as well make them actually Bayesian from the outset. So one of the things talked about in the reading, and if you didn't get your copy of the reading, I have some more up here. We'll be reading like the second half of that for Thursday. It has this fundamental model in polling, I guess, political science by Doug Hibbs. There's actually more to it, but the bread model for presidential vote percentage basically asks what's the relationship between economic vote and votes at the presidential level for either the incumbent or whoever is in the same party as the incumbent, if the incumbent is leaving after 8 years. And there's more to it in terms of overseas deaths due to unprovoked wars and stuff like that. But let's just focus on the growth aspect of it. So we're basically asking the question, how sensitive, or what would be the prior predictive distribution in a linear model for an outcome variable that is, incumbent party president vote share, and the main, or the only in this case, predictor variable is what has been the growth rate of per capita income over the previous 4 years presidential term. So how would we go about thinking about constructing a prior predictive distribution for something like that? That did not work. Okay, so don't everybody answer at once. What are the parameters for, linear model, let's say? That's not an explicit part of the theory, but let's say we're going to estimate this with a linear model where vote share for the president and the popular vote, or the same party, is the outcome variable, and the growth rate in the per capita income is the predictor variable.
Just the intercept and the slope.
Okay, so we've got an intercept, alpha. We've got a slope, beta. What else do we have?
I guess an error term, sigma.
Standard deviation and error term, sigma. Good. Okay. Who wants to talk about some? Alpha. So one of the tricks that we pretty much always want to do with Bayesian analysis is to think about our predictors as being centered, so relative to the average growth rate in the data that we have. That way we can interpret the intercept as the expectation of the outcome when growth is average. And in the context of a linear model, it's not so bad if you sort of fudge that and say, well, what are my beliefs about the outcome variable marginally? What would its average be? So what sounds like a reasonable percentage for the incumbent party, or at least the incumbent party's president, or incumbent party's nominee, if the president gets term limited, like Obama was in 2016. Yeah.
Oh, I'd say that the alpha is pretty stationary, given that the guy that is currently in power had to win elections previously. Mm-hmm. So it's perhaps reasonable to suggest that the alpha is 55.
Okay, certainly a little bit over 50.
Yeah.
So some incumbency advantage a little bit. What are the bounds on alpha?
100.
Right, so it's got to be between 0 and 100. Okay, so we know that. Might have, a median somewhere around 50 or a little bit over. And then, what might we say a little bit about the uncertainty about that? Got plenty of American politics people here. So, what's the biggest value you could imagine being for the expectation of the incumbent party president vote share?
60.
Yeah, really talking basically between 40 and 60. Maybe if there was Vietnam War or something like that, it could go outside of that. So, we basically want to be putting most of the prior probability in that range and maybe a little bit north of 50. Okay, we can do that. Let's think about beta. So the sensitivity of vote percentage to, are you a little bit above or are you a little bit below average per capita income growth? Not a problem. We got that on YouTube.
I would say between 2 to 3%.
2 to 3, okay. 2 to 3. So if, let's say alpha, let's call it 52. If growth were, average growth is going to be around 2% for most of the late 1900s. Expect 54, 55%. Okay, maybe, might sound reasonable. Could it be negative?
Yes, would be.
I mean, mathematically, yes. In political science terms, is there any theory under which this could be negative?
Yeah, but this is centered, right?
Growth is going to be centered, yes.
So 2 to 3 is quite large.
Okay, you want 1 to 2 maybe?
It's going to be 50% of the time, nearly 50% of the time, it's going to be below average if it's going to be centered, right?
So we're not centering the outcome. We're doing it relative to centered growth. So if you're at average growth, then we're anticipating something low 50s. If you had, let's say 3% growth rather than 2% growth, then we're predicting 54, 55%. And if there was like a recession, let's say 0 growth, then we'd be talking 45, 46. That's average over the whole 4 years. So if there was like 0 net growth over 4 years, maybe 45 sounds about right. Okay, possibly. Yeah, so this seems like this should definitely be positive.
So what is the beta again? So like if I have 1% increase in, what is that, like the GDP or whatever?
Yeah, so 1% over average.
Okay, over average.
Yeah.
Going up over those 4 years, then I have 2 to 3% increase in the alpha.
In the expected percent.
Okay.
So above alpha.
Okay.
So if you're at average growth, we think 52, somewhere around there. And if you had 3% growth rather than 2% growth, then we'd be looking 54, 55. All right, sigma. What are the bounds on sigma? Go ahead.
It needs to be positive.
Right. Okay. So this is another one. There's probably some upper bound that we could work out from the fact that the outcome variable is bounded between 0 and 100, but we're just going to be using like a conditional normal distribution because all of the values are going to be somewhere close to the center of it, so we're not going to be running into the edges. Anyway, what seems like kind of a reasonable value for sigma in this context. So given growth, what would you expect for the standard deviation of the error in each election for president?
It captures all of the factors that our model is not capturing at the moment, right?
Hmm?
It captures all of the factors that our model is not capturing at the moment,
Which is a lot of things, yeah.
So one does not seem very reasonable.
One is maybe too small. Okay, so let's say probably less than 5. Okay, so somewhere between 1 and 5 here. All right, not bad. Okay, so that's certainly a start. These can't see that. These sorts of things are often depicted in graphical format, a little bit like this. Not everybody uses the same conventions for these things, so I'll just explain the conventions that I use. So the ones that are circles with gray, these are observable variables. And you should think about this as a depiction of the prior predictive distribution, the model for how you think the data is generated. The ones with the not gray in the circles are unknowns. These are never going to be observable. We got our beta, we got our alpha, we got our sigma there. The arrow means a functional relationship, in this case linear relationship. So mu here is the expectation of the vote. It is in a diamond shape because it's deterministic given the things that point into it. So the growth rate, beta the slope, and alpha the intercept. So I added, in this case, beta multiplies by growth, and then you add the intercept onto that. Not everybody puts the exact functional relationships. And then the squares indicate a distributional assumption, and the lines that go into those squares don't have arrows. They just mean, okay, mu and sigma are going into a normal distribution that generates the outcome, vote percentage in this case. And by the same token, we have prior distributions on each of the unknown parameters. So alpha, we said, has to be between 0 and 100. And so we could use the Johnson quantile parameterized distribution bounded on both sides, in which case we would need to input 3 quantiles to describe our prior beliefs about that. So we kind of said, maybe 52 for a median. What would be reasonable values for lower 25% quantile, upper 75% quantile, if we're going to call 52 the median?
What would be the 40 and 60 that we were talking about? The 40 and 60 we were talking about?
Right. So the theoretical range is 0 to 100 because the outcome is measured in percentage popular vote. There are probably no political scientist who would entertain a model that predicted an incumbent president getting less than 40% of the vote under any circumstances. It may have happened in like the 1800s, but like in our lifetime, that's just inconceivable. And then, it seems very daunting in a two-party system like the United States for somebody to be able to get 60 in a re-election. What did Reagan get against Dukakis? It might have been up there. But anyway. So the practical range, I would say, we have to be putting probably 99% probability it's between 40 and 60. So wait, 25th percentile, 75th percentile?
44, 45, and 56.
Okay. Sounds about right. I can live with that. Okay. Sigma is probably a relatively small number, but there's no theoretical upper bound on a standard deviation. So we could use Johnson quantile parameterized distribution semi-bounded, just from below at 0 like we did on the homework. Had some disagreement, which is okay, about what would be a median there. So obviously you can plug in your own values. If we took 4 for the median, is that 3, 4? Okay. 25th percentile, 75th percentile? 2 and 5. Okay. All right. That leaves beta, which is a slope. Theoretically, could be any real number. Usually, for slopes, we're going to use unbounded parameterizations, and so the one that we talked about, but we haven't had a homework problem on it yet, is using the generalized lambda distribution. In which case, in addition to the median and the 25th percentile and the 75th percentile, we need one more quantile in order to fully characterize that distribution. Although in this case, we should probably be putting little to no probability on the slope being negative, maybe a little bit, just sort of mathematically speaking, but we're certainly not anticipating negative values here. Also had a little bit of a disagreement about that. So between 2 and 3, someone wanted for the median. Okay. 25th, 75th percentile? 1, 3. Okay. And then, upper quartile? Somewhere 4-ish, right? And then, maybe you're going to need like a 90th percentile, as well in order to fully characterize that. So those would be the prior question?
Yes. Why do we do the lambda distribution for beta rather than one of those JQPD something or other?
Right. Really a Johnson quantile parameterized distribution that anyone knows of yet for a random variable that can be any real number. And so there's some other distributions. I'm not entirely sure which one would be best, but anyway, generalized lambda distribution can be defined for any real number. So we will go with that. All right. So in order to use the generalized lambda distribution, we're going to have to solve for the asymmetry and the steepness parameter. I put in more skeptical values than you all. Historically speaking, these would be too low. I was sort of imagining what I think the sensitivity is like now in the election coming up, but that may not fit the historical data as well. Also, I mostly wanted to illustrate this, like when you solve this thing, you may get a warning message saying this generalized lambda distribution, which can be defined over the entire real number line, it got a value of the steepness that was so steep that it actually truncates off the lower tail, in this case at negative 2.9. But since we don't think negative numbers are particularly plausible anyway, the fact that we're cutting off negative 3, negative 4, negative 5 isn't worrying me too much. It does go out to infinity in the positive direction, so that's maybe okay. So you'll get these warnings if your generalized lambda distribution actually turns out to be bounded on one or both sides. But anyway, this is the asymmetry and the steepness values that were consistent with the quartiles that I put in which case we're ready to go. I also, my sigma prior beliefs were more, I guess, optimistic than yours, in that this would, not have as much error. But yeah, 52, 48, 56, something for alpha is, I think, pretty consistent with what you have. So if we get the data between like 1950 something and probably the Obama-Romney election, maybe the Trump-Clinton election, there's 16 elections over some relatively recent time period. So we can do this 10,000 times to draw from our prior predicted distribution. We draw sigma from semi-bounded passing in the quantiles for that. We draw alpha from a bounded Johnson quantile parameterized distribution, draw beta from a generalized lambda distribution, need to give it the interquartile range, so that's the difference between the 75th percentile and the 25th percentile in addition to the asymmetry and steepness parameters that we solved for. That gives us a conditional expectation, alpha plus beta times the growth rate. This is going to be messed up because I forgot to subtract the average, but that's the idea. Then the error term epsilon is drawn from a normal distribution with mean 0 and standard deviation with the realization of sigma that we have. And then the outcome that we observed is the sum of the sort of systematic component, which is represented by the conditional mean mu, and the unaccounted for term, which is represented by epsilon with that standard deviation. Sum those together, and we get our prior predictive realization of y. So this normal distribution that we're going to use for the likelihood refers to the conditional distribution of y given mu. In other words, it refers to the distribution of the error, not to the marginal distribution of the outcome, the conditional distribution. Anyway, that's 16 by 10,000. We could look at its shape, make sure that this looks reasonable. But basically, in simple models, if you're using quantile parameterized distributions, you ought to have, a pretty good sense as to what the parameters are. And in like a linear model, nothing too crazy is going to be going on with that. If we wanted to see how this might be done in Stan code under the Hibbs or half the Hibbs model, that we would have the number of time periods, the growth rate relative to average, and the outcome variable between 0 and 100 for the percentage of vote. Then we have a bunch of constants for our inverse CDF transformations on the 3 parameters. And also, if we want to make a prediction as to what would be the vote share for Trump in 2020 under some assumed growth of per capita income over the whole first term. We don't know what 2020 is going to be yet, but we might have some forecasts or something like that. Then in the parameters block, we declare a vector of 3 p's between 0 and 1, representing the cumulative probability of each of our parameters that we transform into in the transform parameters block using the inverse CDF functions that are defined in the external file that we #include in quantilefunctions.stan. So alpha, we apply the inverse CDF for the bounded distribution using our quantiles. Beta with the inverse CDF of the generalized lambda distribution. Sigma with the inverse CDF of the Johnson quantile parameterized distribution, semi-bounded. Then we get our 3 substantive parameters that go into the conditional mean function for mu, and then mu goes into the likelihood function for evaluated at the observed outcomes, also the sigma that comes along with it. So if you were going to do maximum likelihood, which is never a good idea with 16 observations, it's not that great an idea anyway, but if you were going to do maximum likelihood, then it would be pretty much all the same stuff to get to the likelihood function, and then you maximize it, relative to the parameters. Now, there is an extra step in our case where we're, choosing transformations, and those involve prior medians and whatnot. But if you have a halfway decent understanding of your problem, then it's not too difficult to come up with quantiles that are, not crazy. And then those are going to help inform the estimates, particularly in situations in which you don't have a whole lot of data, which for our case is. Then if we want to draw from the posterior predictive distribution for what the model predicts Trump's re-election percentage would be, now we're just using this one value that we pass in as data for the Trump growth rate, and then we're drawing from that normal distribution based on the posterior parameters and that. But it looks like the growth rate of per capita income under Trump is going to be essentially average. relative to recent history, and so we're mostly just based on the posterior distribution of alpha. Questions?
Explain what is it in the matrix, like, so 16 is like every election, and then every column is like a draw from the posterior distributions. What is the 10,000 thing?
Prior predicted distribution, yes. So there's 16 elections. And our beliefs about each of those 16 elections with 10,000 draws. So I could make a histogram of any one election, and it would sort of say what our model predicts the vote share to be for that incumbent in that election, given the growth rate over his previous term in office. Shall I do one?
It's just like, do you have like for every, it's like one paper is like the full model is like in each column?
Yes.
Okay.
So each row is an election, but it's our model's prediction for that election. It's going to have a whole distribution, so we're not certain about it just given the growth rate. And so you can imagine a histogram or something among those 10,000 draws that's going to be in the vicinity of 50, maybe a little bit higher, maybe a little bit lower, depending on what the growth rate was for the previous years of that term. Should have probably put the histogram up, but you can do whatever you want with those to verify that your predictions are reasonable. However, in a simple linear model, that essentially comes down to, are your priors reasonable? But it's two sides of the same coin. If your priors are pretty reasonable, then your prior predictive distribution of the outcome will tend to be pretty reasonable as well. But since this is observable, a lot of people are more comfortable evaluating, like, is my prior predictive distribution reasonable? If so, my priors couldn't have been that bad.
If for each of the 16 elections, there's 10,000 simulations in which each of the three parameters are varying according to their distributions.
Yeah, they get drawn new each time. Good.
And then that would be used just to, like, if you have a question in the audience, like, is the prior like accurate? You just show the histograms, but it's not used in StanArm, so it's just like to show that your prior
Right.
is nice.
Yeah, this is kind of a preliminary step. If we were to do this in Stan, then we're going to be passing in actual vote data. And now we want to update our beliefs about alpha, beta, sigma relative to what they were here to what they are after conditioning on the data. Okay. So, you could draw from this in Stan. We've seen one of these examples before. Get a whole bunch of draws back from the posterior distribution. So my posterior beliefs about alpha did not change or did not shift that much. They certainly got more precise. So now my 25%, 75%, 51.3 and 52.68. So they did get concentrated, but it basically did not shift from a median of 52. So data gave us more certainty, but we were basically got the median right to begin with because that wasn't that hard or wouldn't be that controversial among people who know a little bit about American politics at the presidential level. Yes?
So what would this look like? We made like a really artificial value or we put really artificial value for alpha, like something unreasonable. Then what would the model look like? Like it would give us something that is more accurate, and we would have to update our prior? Or?
Yeah, so if 70 or something like that, then this posterior mean, posterior median would be much higher because it's a compromise between the prior and the data. But you can sort of see that with the beta. So I put in a median of 1. And even with 16 data points, it shifted me to a median of 2. Some other people who probably know more about American politics than I did, would have preferred a prior median 2 or 3, in which case it would have shifted them less. So even with 16 data points, you can get a pretty good shift. So I think people don't understand how easily it is to move off priors if you have a decent model.
Are these three parameters, I mean, they should seem to be dependent on one another, right? In what way was that taken into account in what you did?
Specified the as being independent of each other, and that is kind of reasonable for alpha and beta. In these cases, I think independent priors could be defended, but as we'll see in the next, the posterior distribution conditional on the data, it's a joint distribution. They are going to have correlations and other form of dependence among them. And I should probably be taking that into account going forward, because now my beliefs about these things are not only more precise and in some cases shifted over, but they're also correlated now after having conditioned on the data. Sigma came back with a posterior mean of about 4, which I think that's what you all were saying. I was lower. Yeah, I was putting median to upper quartile at 4. So a little bit of a shift there as well. Anyway, beliefs get updated. Linear model, kind of easy enough to understand. You can plot the two-dimensional planes among all of these parameters. So you can see, particularly with the beta, the sensitivity, still a lot of uncertainty about it. So these are marginal histograms down the diagonal, but also skewness to it. There's a little bit of possibility it could be up around 5, not much, but basically none that it's negative. Okay, that kind of makes sense. Other sorts of things. You can look at something like this or like this to see the sort of two-dimensional distribution of alpha and beta. Since this is a intercept and that's a slope, they shouldn't have too much to do with each other. You do see a little bit more negative correlation between the slope beta and the error standard deviation sigma. So if beta is out in its tail a little bit, 4, 4.5, then sigma tends to be lower, because these are negatively correlated a little bit through here. So it's basically saying if the sensitivity is higher, the signal is higher, the noise is less. But a lot of uncertainty in estimating both of these. Not a whole lot going on in this particular case, but when we get to more complicated ones, we do want to be looking at this pairs plot to sort of get a little bit of a sense of the multivariate nature to this joint posterior distribution that we obtained, because the numerical summary is just margin by margin.
So after looking at the pairs plot, I'm just wondering, like, with the error from earlier about it being like cut off for the negative values, like what's the sort of like substantive difference from like having like pretty much like 0 weight on expecting beta to be, say, like 20, and it like literally being cut off at like -3? You know what I mean?
So the prior would not have allowed it to be lower than -2.9. In which case, if I happen to see, posterior distributions being like all bunched up at like -2.8, I would be worried that I, made a mistake or something like that. But it could not have possibly given you a draw of -3. Now, in theory, it could have given you a draw of 30, even though, like, for substantive reasons, I'd be worried about that too. But the highest one probably came out at like 6 or so. But in any event, very unlikely. Certainly, if you wanted to make some conclusion about political science as a result of this, you would want to be talking about mean median rather than like it could be 6, like 1 draw out of 4,000, something like that. Okay, so that is a linear model. Now, since we have a little bit of, or hopefully a decent understanding about that also from the reading, it's possible to sort of write a pretty generic linear model Stan program that could work for any set of predictors, any number of predictors. And so we want to take this to a more complicated example. Think about what affects the wholesale price of diamonds. So anytime you're talking about diamond or prices of anything, you're ordinarily going to have to consider simultaneously supply side and demand side. We're going to call the short run supply of diamonds fixed. Certainly the supply of diamonds in the ground is pretty much fixed, although companies could exert more or less effort digging them up. But anyway, we're just really going to be thinking about the demand factors that explain the variation in the prices of diamonds. So let's think up a halfway reasonable, linear in its predictors model for diamond prices as a function of diamond characteristics. Size. Okay, we've got the length, the width, and the height, basically. Okay, we're going to want to be considering those. Carats, which is a measure of the weight, which is going to be related to the size, but also like the density of the carbon molecules. Whatever. Yes.
No, I was just thinking of like clarity of flaws in the diamond.
Clarity, good. Country of origin, okay, we don't actually have data on that, but that is something that you would think about. It sounds like it would be a supply side thing, but it's actually a demand side if there's sanctions and whatnot. So yeah, relevant consideration, don't actually have data on that in this case. Cut.
And color, maybe?
And color.
Yeah.
All right, good. Okay. So if those are the main predictors that we need to be thinking about, how will we think about putting that into a linear model, and if so, priors on the coefficients of those sorts of things? Or a model that's linear in its coefficients, at least.
Maybe for things for the variables related to size, carats, and clarity, you would expect just like a positive beta value, and then for cut and color, that would be categorical.
Mm-hmm.
So we might want to have different variables for cut and color depending on how many categories we have.
Right, good, exactly. Okay, so for those of you who are economists, what do we almost always do with price variables to transform them? Log. That essentially converts a multiplicative relationship. So if I were to increase the carats by whatever, it would increase the price multiplicatively to something that could be additive. And also for things like diamonds, which have extreme skew to it, this mitigates the influence of outliers for like $1 million diamonds that happen. So I do think it's going to be a good idea to think about the logarithm of price, in which case you have the choice, but one that's often made, to also take the logarithms of the continuous predictor variables that are positive, in which case we can interpret the coefficients for a predictor variable in log form as elasticity, yeah. So for like a 1% increase in the weight or whatever, 1% expected change on the outcome. Okay, good. So yeah, for most of these things, we should be expecting a positive effect. And in elasticity terms, what would be kind of reasonable-ish magnitudes for coefficients in a log on both sides model? So like, would a 1% increase in carats, do you think, yield a 10% increase in price? It's a little bit probably too much sensitivity. Yeah, so I would say usually when economists think about elasticities of things, they're thinking sort of small-ish one-digit numbers. You know, 1 for 1 would not be implausible. Could be less, could be more. So we should be, you know, thinking about kind of 1%, 2% sort of deals. But and here's the variables we actually have to work with in the diamonds package. It has a whole bunch of these. These are wholesale diamonds. I did mention that. So this is before they actually get to the diamond store. We got ordered factors for cut and color and clarity and things like that. But basically, once you get beyond like a couple predictors, it's difficult to even think of like a comprehensive prior. And so that's why it can be good to try out different things and then look at the prior predictive distribution. But, and you know, something like this, maybe even more common or more complicated situations in which you have maybe so many predictors that it's difficult to think about priors on their coefficients simultaneously. You sort of have to start thinking about what's the distribution of coefficients collectively. So, you know, we're thinking kind of small-ish positive numbers for most of these things. But that's even before, like, there's no reason why our model has to be linear in X, Y, and Z, which are the dimensions of the diamond. There could be interactions there. So we need priors on those. That makes it more complicated. So what the StanLM function and the RStanArm package does in an attempt to make this easier for you is to ask, what do you think would be the R squared for a linear regression involving like the logarithms of some of these predictors on the logarithm of price? Question?
Deal with collinearity like in the Bayesian framework. If you have two very correlated, like do they have like the same distribution? Like how would you?
Principle, you would want to use a bivariate prior because your beliefs about the coefficients of two, let's say, highly positively correlated values shouldn't be independent of each other. But we've kind of only learned about bivariate normal, and even that's not supported in RStanArm. So basically, for the purpose of this week, restrict yourself to thinking about univariate prior distributions. But what I'm saying in the case of StanLM is that if you can tell me what you think the R squared is, the rest of the priors are hard-coded. So conditional on the expected R squared or whatever, then there's a maximum entropy prior on the coefficients, an improper uniform prior on the intercept, and a Jeffreys prior on the scale parameter. And those are all hard-coded. So the one piece of information that you as the user have to supply is, what do you think the R squared for a regression like this would be involving log price of diamonds in like these predictors?
So what is actually the output? So what are we trying to predict or?
The logarithm of the wholesale price of the diamonds.
Okay, so it should be high because we have like a lot of things that like basically affect the price.
We got a lot of things. I mean, certainly in the era of big data, like there's not millions, but we sort of think that we have the main things, excluding the country of origin, which may be under like sanctions and stuff like that. But so you're saying high, can you be like more numerical?
So I think for example, from 0 to 1, like 0.67 or like above 70, let's say.
Above 70? Okay. Any other diamond experts? 0.7, 0.8? 0.6. Okay, was that a mode, a median, or a mean? You're going mode. You get the choice if you have more than two. For the same mode? All right. Anyway, okay, so that is what you need to put in. Oh, one thing before you do that. R, this is the most bizarre thing about R, and there's a lot of bizarre things about R. Ordered factors are handled differently in regression model than unordered factors. And the default way of handling ordered factors is this thing called Helmert contrast. Helmert did not program them himself. I have been able to ascertain that. I have never found anyone who could know the definition of what those are, or why it should be the default, or why it should be different from the way dummy variables are handled for unordered factors, which is the usual way we think about it in social science, like a dummy variable and then the reference category gets excluded, like whatever is the lowest one. So if you do this once on each computer you use Rn, it will set them to use like regular dummy variables for both ordered factors and unordered factors, in which case you shouldn't get confused by the output. But you just have to do this once, and you may have to restart R in order for it to take effect. This .r profile file is basically a file that R reads when you start R, and so you can change some of the settings and the options and whatnot. Anyway, need to do that before you start estimating regression models. So the StanLM function in the RStanArm package will estimate linear models in much the same way the LM function that comes with R does. Takes the same syntax of a formula in the R syntax, a data frame for where the variables live. The only difference is we need to specify priors, and in this case the only prior to be specified is on the R squared. I went with a prior mode of 0.8 in the formula, so you can take the logarithm of price, provided all of those are positive. You can use the asterisk to create interactions between the caret variable and the logarithm of each of the width, height, and depth thing, etc. And then the factors for cut and color and clarity just come in additively. They're going to get made into dummy variables. When you get back the results, it's basically a glorified matrix, 4,000 rows, in this case 28 columns, because we had 28 unknowns that we're getting the posterior distribution of. You can call as matrix, as data frame, whatever, to get a two-dimensional representation of those, so you can see, you know, some of those values. But if you sort of just leave it as a object that StanLM produces, then there's a lot of other methods that are defined for an object like that. But you can always get at the underlying draws if you need to. So anyway, we get this 4,000 draws on 28 variables. Posterior distribution conditional on the model that we specified in a prior mode of 0.8 on the R squared. If you just print it, typical output will look like this. You'll get a posterior median and estimate of the standard deviation based on the median absolute deviation from the median, which is a little bit more robust, a lot more robust to the tails of the posterior distribution than the regular standard deviation would be. Usually when people talk about medians as their sort of measure of centralness of a distribution, they talk about median absolute deviation from the median as their measure of spread rather than standard deviation, which kind of goes with the mean. Now you can calculate the posterior means as well, but the default output involves the posterior median. It's less sensitive to the tails, always exists, sort of corresponds to what we imagine most users of RStanArm think of as like the center, particularly for asymmetric distributions. The mean and the median, not the same thing. So you can see median coefficients on all of these things. It actually updates our beliefs about the R squared to a median of 0.98. So it seems as if, at least at the wholesale level, there's basically a formula for diamond prices that has very little noise in it. And we've kind of rediscovered that formula. But if you had like a wholesale diamond store, you would probably know that from like the bids that you were getting from the suppliers or whatever. So this is actually fairly deterministic. But we had to learn that from the data. Questions? Oh, 2 questions.
I don't know if this is the case in this data, but when we're taking the logs and there are zeros sometimes, right? Like that'll cause an issue. So is that being automatically handled here?
No. So all of these prices were positive, so did not encounter that problem. There was like a couple observations where Z was 0, I guess, to the amount they measured it, like the diamond had no height. That was probably a mistake. But anyway, I did subset Z greater than 0 to exclude those couple values. And so then I could take the log of Z just fine. So yeah, like if you're taking the logarithms, the thing should at least be conceptually positive. And anything that gets excluded as a result of that was probably a mistake in the data in the first place. I think Paul had a question.
How susceptible is that posterior R squared to the prior that you put into it?
In general, it could be more or less. We're dealing with almost 54,000 observations. So I think you could have put in like 0.08 and you probably would not see like a noticeable difference in the posterior distribution. Because with all that data, whatever your beliefs are going in are going to get shifted, unless you already knew the truth. They're going to get shifted a lot. Now, 50 observations, obviously, is going to be a lot more sensitive to prior. But not only did it shift it a good bit, it shifted it like very close to 1. So even if you didn't think, oh, there's some deterministic formula that the market is using to price the diamonds, it seems as if it was there in this case. You'd see the same sort of thing with like houses. Like you may not really know what a house like should cost, but the real estate agents do, and they at least have kind of a mental model. Like if this house is worth, that sold last week is like worth this much, then a house on 1 block over that's like a little bit smaller. Like they kind of know the formula, and so you can see this sort of thing in a lot of different markets that are actually more predictable than you would have predicted under your prior.
And so I suppose the intuition behind assigning an R squared value is that it then produces, it optimizes all of the other parameter values such that it would account for that percentage of variance in a linear model. Is that the idea?
Yeah, so as I alluded to, the prior on the actual coefficients is maximum entropy for a given expected R squared.
Yeah,
So
okay.
if you imagine like all collection of coefficients on like 26 predictors that have an expected R squared of 0.8 is maximum entropy over that prior distribution. Now, of course, the posterior distribution can be, whatever, because we condition on 54,000 observations. But that's the starting point.
Do you have a question?
Yeah.
Mike, another question?
On the, I think it's the previous slide where what is the adapt delta doing something for the prior? Or is that just like some other
That's
arbitrary
the
thing?
tuning parameter. Don't
Okay,
worry about that
cool.
right now.
Okay.
So moving along, if we do summary, it'll calculate posterior mean, standard deviations, some more quantiles. Also at the bottom, it got chopped off here, but there would be effective sample size estimates. We want to make sure those are pretty good. Although there's a special function to just pull those out in relation to the nominal sample size. So you can see there's some variability here, but certainly for the cut dummy variables, we're getting effective sample sizes that are like 25% more than the nominal number of draws, which is 4,000, due to this super efficiency of Stan. For something like R squared, it's only about half, but that's still way good in comparison what we saw with the Metropolis Hastings and the Gibbs sampler the other day, where we were getting ratios of like 0.1, 0.2. Sometimes we're getting above 0.1, but rarely are we getting, in this case, less than 0.5. So we're getting plenty of effective draws. Those draws from the posterior distribution did not have that much dependence, which is good for doing the estimates. So posterior interval function that takes a probability for the width. This is basically, in the case probability 0.8, 0.4 to the left and 0.4 to the right of the median. So an interval centered on the median that captures 80% of the posterior probability on all of these coefficients. So these are what people think confidence intervals are when they do something frequentist. Like they think, okay, there's a 95% probability it's between here and there. In fact, that's not true. What it means is confidence interval is this function, and if you apply that function across 1 million data sets, in 900,500 of them, would you expect those confidence interval bounds to catch the true parameter? But those confidence interval bounds are changing each time. So conditional on the one data set that you have, here are 80% intervals that capture 80% of the posterior probability. You can go out to 0.9, 0.95, but when you're doing like 4,000 draws, the endpoints of extreme tails are not estimated with great precision. So if you wanted to do something like that, you would probably want to up your number of draws. But anyway, I tend to do like 50% intervals, 80% intervals to be able to say, something like for ideal cut relative to whatever is worse than good, which I think is fair or something like that. There's no bad, even though fair is the worst category for cut. I would say there's an 80% chance that the expected change in the log price would be 0.16 and 0.17. So that's the sort of thing that people say about frequentist confidence intervals with no justification. But anyway, posterior intervals is what will get you those, and you can put in whatever width you want. Also, if you evaluate what is the proportion of times where the draws are positive or negative, you get what people misinterpret p-values as. So this is essentially saying what's the probability that the coefficient is positive, and then 1 minus that is the probability that it's negative. So we're no longer testing that it's exactly 0 for a null hypothesis against like a one-sided alternative that it's positive. We're just saying like what's the posterior probability that it's positive versus the probability that it's negative. So now we're thinking about two intervals rather than a point in an interval, which is kind of weird. Anyway, all of these are either 0 or 100. So like all 4,000 draws of the cut ideal coefficient came out on the right side of 0. None of them were negative. Some of the other ones like color I don't know what color I is, but we're almost positive that, almost sure that that has a negative effect on the log price. Basically, the only one that had any variability was this log-fish ratio, which isn't even really important. But in other situations, you would be able to say, okay, this thing that is sort of theorized to be positive under the posterior distribution has a 98% chance to be positive and a 2% chance to be negative. And that is a lot more reasonable conclusion. Final thing, so you might look at these coefficients and say, well, how can I interpret any of that when I've got all these interactions going on? It's in log price, and I want to say about dollar price. And so really the answer to these questions, like how would you interpret this thing, is you don't. You make a plot not super focused on what is like one coefficient. You want to evaluate the implications of your entire model. And this can be done relatively easily. So we call posterior linpred to get the posterior of mu, but that is going to be relative to log price, not dollar price. So we EXP that to get the expectation of the diamonds for the existing data values that we have in dollars. And I divide by 1,000 to put it in prices of $1,000 rather than $1. Then I create a copy of my original data frame that has the same observations. And I say, well, what if I increase the carats by 0.2? They like recalibrated what a carat means recently for some reason. Anyway, I think that's like 1 gram increase or something like that. Small-ish, but okay. And then we recalculate what the mean would be with new data equal df, the thing that we just created, where we bumped up all the carats. And then exp that and divide by 1,000. And so now we're just going to look at the implications of our model. How much did the simulated price in dollars change when I increased everybody's carats by 0.2? And you make like a graph of that. And it comes out to be this estimated density function. So it's going to have a mode of like $900 or so. Certainly has an extreme tail, but it's never negative, whatever. It has like this plot. Because even if you're estimating a linear model, if your outcome is in log price, then all you can say just by looking at the coefficients, this is the expected difference in log price. But that is not particularly meaningful except to economists. For most of the rest of the world, you want to explain it in terms of dollar price, and that is going to have a nonlinear relationship because you did a nonlinear transformation. But anyway, so basically for whatever you want to say, you can just basically do this counterfactual on your posterior muse, and you can put the transformation so it's back in like world units, even if you had to make some transformations in order for a linear model to make more sense. But anyway, we can get sort of the mu for the data as they are, and then what would the mu be if all the carats were increased a little bit, and then we get the difference and we can plot out or histogram out whatever, a distribution that looks like this.
What are the arguments in the posterior linpred function?
So basically the thing produced by StanLM, which I called post, which is going to have 4,000 draws to it. That kind of takes a little bit of time to deal with. So I said only use 500 random subset of the draws in order to make this like aggregated plot. There's a couple more, but those are the main two, like the posterior object that created and how many draws you want to take from it. If you don't give it a data frame, it just uses the old existing data frame. And then, but you can make this hypothetical data frame based on the old data frame, and then everybody's carats are more. And then like just plot the difference of that however you want. So for all but like models that are as simple as Hibbs, there's going to be some challenges in interpreting the results, and those challenges can be overcome very well in a Bayesian model by evaluating the implications of the whole model using graphs and acknowledging the fact that there's going to be uncertainty. You don't know exactly what the estimated effect is, but we are like very certain that it's positive, and we can talk about posterior mode, posterior median, posterior mean, etc. of these things, but we can sort of capture all of that. We just use a plot. Anyway, we'll pick it up on Thursday, talk about regression models for like not continuous outcome variables, generalized linear models. also using RStanArm. So read the rest of the reading if you already got your reading. If you haven't, I have like a bunch more copies here, which probably should not be the case. But anyway, see you then.